7-segment LEDs here, and this module interfaces to the A to G LED segments and the enable digit line. So now that I kind of did a very generic overview of how all this stuff works, we're going to dig into the actual VHDL and kind of quickly derive these devices. We're going to add the Mercury ADC and the Yavaja to the project, and then finally create a top level to contain all these modules. So kind of like in the past, I explained what these modules are going to do in the top level, and then in the VHDL component of the video, I explained how these components accomplish what they do. So before I start, I'm going to say that for these 3 pieces here, since they're kind of tedious to implement in VHDL and it'd be kind of a pain to wire all this up in the top level, what I'm going to do is I'm going to create a surrounding VHDL module that encapsulates the functionality of all 3 of these components in a single VHDL module. In the past, I've shown that a VHDL module has a process that helps carry out the logic. Well, you don't need to only use one process in VHDL per VHDL module. You can use as many processes as you want. And so in this case, I'm going to use a process for each one of these components. So just kind of heads up on that, that's what I'm going to do here. I already have all the VHDL implemented. To save on time, I'm just going to step through the design that I made, so that way you can understand how this was developed. But first, I'm just going to explain how I hooked up the Mercury ADC and how I hooked up the Yavaja project, which is here. The Yavaja in this case is called the VGA controller, which is this component here. In the section where I wire the inputs and the outputs to these devices, for the Mercury, I had a clock connected to the clock pin of the FPGA. The clock pin isn't shown in this diagram for simplicity, but it's there. And this clock is meant to hook up to the 50 megahertz clock on the FPGA. Trigger connects to the clock slow, which is a signal name of the clock to 86 output. It then connects to 1, like I said, channel connects to 5. D out connects to SD out, which is going to go to this register, and out to low connects to the low signal of the register. And these ADC, MISO, MOSI, clock, or chip select and clock, those are the SPI pins that interface to the ADC and are the inputs and the outputs to that SPI interface. And as you can see, they're up here. And those are simply declared in the UCF file here. So that's how the Mercury ADC is hooked up. The VGA, the Yavaja project, is hooked up with the clock input up here connecting to the FPGA clock, the 50 megahertz. Reset connects to the user button, which is the name of the onboard Mercury button. The output horizontal sync connects to the H-sync output in the UCF file, and the V-sync output of the UCF file connects to the vertical sync output of the Yavaja. Output V-sync connects to V-sync in the UCF. The output red connects to signal red, output green connects to signal green, output blue connects to signal blue. And then kind of like what I said before, these output colors are only 1 bit each, so output red is only 1 bit. And I wanted this output red to connect to all 3 pins for red on the VGA. And you can see I did that here. Red, the red top level output, 2 down to 0. These 3 pins are all connected to the 1 signal red, single bit output of the Yavaja. And the same thing for green, and the 2 outputs for blue in the top level, that is connected to the 1 signal blue output of the Yavaja. The input wave data connects to the register. S-wave D is the name of the signal. S-go connects to the I-wave enable, the right enable pin here. That's the signal name for that signal. The name for the signal is S-go. And for the wave clock, I just connected that straight to the same clock that this pin is hooked up here, so the 50 megahertz FPGA Mercury onboard clock. Then finally I have the S counter out, which is the name of this green signal here. This green signal connects to the address in to determine at what address do I write a waveform data point to. So as I mentioned, I'm going to take these 3 individual components and make each one of them a process that's embedded in a single VHDL module. And the single VHDL module here, it's called the FSM Yavaja controller. And the inputs and the outputs are here. And if you look at clock input, reset input, input from the analog to digital converter, the output go signal, which connects to the wave right enable, the output trigger that comes from the clock to 86 process, and that's going to connect to the Mercury ADC, and the output address coming from the counter to hook up to the address on the Yavaja. Now notice I don't have a stop signal input or output because the stop signal in this case is completely internal within this module. So if we look here, I have the clock to 86 process, the finite state machine process, and the count 800 process. And I'll just go through each of these really quick. Clock to 86 activates on clock signal on the rising edge of the clock. If the count is less than 43, then increment this signal value. Now when it gets to 43, set back to 0, and then not this S clock to 86 signal. And this S clock to 86 signal is going to be driver for the signal here. And you can see bottom it connects to the trigger output on the VHDL module. It connects to trigger. That's 43 because I'm nodding, and it takes 2 not operations to make an entire period. So in order to divide the input clock by a factor of 86, I need to count the 43 twice. Now moving on to the FSM. As in the lesson 2 video, I'm using a finite state machine, which just consists of 4 really simple states: an initial state, wait for start state, state go signal, and state stop signal. Starts off at state initial on resets, and on power-ups, it will start off in this state. And so just make sure that the go output is low, so we're not writing any data to this Yabajah. And we're going to go immediately to the next state, the wait for start state. And this simply just waits for the start bit on the UART signal that's coming in from here. So I take the lower 10 bits, and to check for the start bit, I check if the input is greater than 200. And you might think that I want to check if the start bit is less than 200 because I'm checking for the start bit. So I'm going to be looking for the falling edge. If this is the UART signal, I want to look for the falling edge. But in reality, what I did was with this register, I actually inverted the signal, so that way if I get a high value coming from the Mercury ADC, that it outputs as a low value, because on the Yabajah, a data value of 0 is towards the top, and as you raise the data value, you get lower. So if this is your VGA monitor, and you're increasing data and address at the same time, like I said before, it will decrease. So 0 starts off at the top. And so what I kind of wanted to do was invert that. So I used this module to invert the value coming from here. So that's why I check when the ADC is greater than 200. Then I move on to the next state, which it's at this condition that I know that the start bit has been received. Otherwise, just stay in this wait for start state. Then in the next state, just raise go high to make the signal high, enable the right enable, and then go immediately to the next state. And then all this does is just wait for the stop input coming from here just to go to 1. And then once it hits 1, then it knows that it's done capturing, so it's going to go back to the wait for start. Otherwise, just stay in the state. The last process is the count 800 process, which obviously represents the count 800. And so it's going to control the stop signal, which goes to the FSM, and the address output. And so in this case, it actually triggers on the signal clocked at 86, which makes sense because in the diagram, it's driven by the slow clock outputted by this module. Now in this process, so it activates every time S clocked at 86 gets changed, it checks for the rising clock edge of the signal. So if S signal, or if the signal go becomes 1, which means that a start bit has been detected, then check to see to make sure that the S wave address that gets written out here, you can see S wave address gets written to the output address. Check to make sure that you're below 800, and if you are, increment S wave address by 1, and keep the stop signal out here 0. But then once you get to 800, then raise the stop signal high, so that way this FSM knows to lower the go signal back down to 0, so that way you're not writing to the monitor anymore. Then once the go signal goes back low, then we want to reset the address output coming from here back to 100. This is 100 in binary, and just keep stop low at that point. So it kind of makes sense because the Mercury ADC and the count 800 are synced at the same time. So this Mercury ADC begins a conversion at the same exact moment that a new address is written into this input. So that means for every instance that the Mercury ADC is triggered, the result of that process will get written to the data to Yabajah. So I think the next component I'll go over is this register right here, which is the only part left of this oscilloscope application. So really just with these 4 modules, I have the oscilloscope application. The other 4 handle the UART to 7 sites. And that guy is here. It's kind of your typical register. It takes 10 bits in and 16 bits out. And I'll show you why in a second. So on reset, it just resets the data output back down to 0. If load goes high, then 512, and then I concatenate a 0 and 9 down to 1 of the input data that comes in from here. And the reason why I go 9 down to 1, I'm basically just dividing the analog to digital converter by 2 and concatenating the 0 so it's still the same length as 512 in binary. The reason why I do this is just through testing. I found that the result from here was way too sensitive, so I divided it by 2 so that way the waveform would fit on the screen, because what I would get is I'd have this as my VGA monitor, and so the UART signal would just be off the screen. So by dividing it by 2, I was able to get it to fit within the boundaries of the screen here. So that's why I divided by 2 by shifting it down. And I inverted it by subtracting that value from 512. So that's all there was to it to the oscilloscope application. you could see that even though it looks pretty complicated, actually in reality it's pretty simple. So now I'm just going to go over these last 4 components, which takes the digital UART signal waveform input and interprets it and displays the value onto the 7-segment display. And as you saw in the demonstration earlier, that what it does is it will display the most recent value received on the less significant byte end here, and then the previous UART signal will be stored here, and it just gets shifted in. And that's actually fairly simple as well. So I'll start off with the sync hardware, which takes the asynchronous UART signal and makes it synchronous to the 50 megahertz clock. And that component here is called the FF UART RX sync, and the reason why it's FF is for flip-flop. And basically all it does is it has these 2 signals which are initialized at 1, and on reset it's also initialized at 1, so you might be kind of wondering why it's default high when I explain it here. I want to make sure that the output coming from here is high for the UART signal and not low, otherwise the RX UART would interpret the low value as a start bit. So on every rising edge of the clock, what happens is it takes the input. UART RX is this input, and it has clock and reset as always, and then the output UART RX sync is this output. So what happens is this input gets passed to the signal, and that signal gets passed to the FF2 signal, and then FF2 gets passed to the output. Be kind of confused by this because you might think that, well, what's the point of having this? Why don't you just assign UART RX directly to FF2? Well, if this is something that you're confused on, that means you're still stuck in the software mentality, and you need to remember that this is hardware. So what's happening is that both these instructions are being executed at the same exact time. The FPGA doesn't execute this one first, then execute this one second. Both of them happen simultaneously. So it kind of acts as a shift, basically. UART RX gets shifted into FF1, the same exact time FF1 gets shifted into FF2. And kind of like how I explained before, how if these red are your rising clock edges, and this is your asynchronous waveform, I mentioned that it's 2 clock cycles behind, which makes sense now that you see the application because you have 2 signals. So on this clock edge, this green is being passed to FF1, and then on this clock edge, FF1 is being passed to FF2, and FF2 goes to the output. I'm going to move on to the RF UART module, which will take the synchronized UART signal, and when it's done parsing that signal, then it will take the resulting data byte and store it in this register. So this is the RX UART module, which carries out the RX UART component there. It has the input UART RX, which is the synchronized input here, clock and reset as always, and then the output RX data, which is, you can see it's a byte long, and then the load signal to signal the register that's connected to it here to load the data byte coming from. So it has an initial state, start bit, so it waits for a start bit here, then it waits 1.5 baud, samples a bit, counts to see if it's received 8 bits, waits another baud, then it has a cleanup state, and it waits out the stop bit state. So it's got the asynchronous reset, so on every rising clock edge, starts off in the initial state, then goes immediately to start bit state. So it's input UART RX, which again is the input coming in here, it's going to wait for that to go to 0 for the start bit. And until that goes to 0, it's going to stay in this state. Okay, so then after we move from start bit to wait 1.5 baud, which will happen once we receive that start bit, we'll get here. So what's going to happen is that in this state, it's basically kind of a delay where we want to wait 1.5 baud lengths. But why do we wait for 1.5 baud? Well, we have to remember that we're starting this state right when we receive our start bit. So let's say that this is our input waveform, the UART waveform that's coming in, and that this is the start bit. And this is the start bit, which waits for 1 baud length, and then the first data bit. Well, what we want to do is, since we're starting wait 1.5 baud right here, we don't want to wait 1 baud length, because then otherwise because the next state is going to be sampling, and we don't want to sample this waveform right at the edge like this. We want to make sure that we're sampling the waveform right in the middle of the first data bit. So when this state is activated here, it's going to wait 1.5 baud lengths. So that way, when it exits out of this state and goes to sample bit, we will be at a time where the middle of the first bit is currently on the input. So it just uses this baud counter and counts to a constant, which is set at 1.5 baud, and then it goes to sample bit, and it resets baud count to 3 because we have to accommodate for these extra states that we're entering in, because if I set it to 0, then I'm wasting time going through other states. So I want to accommodate for the clock cycles which are being taken off by this state, the count 8 state, and the wait baud, or in the wait baud state here. So what's going to happen is that there's this SUART RX data signal, which will be shifted in with this input. So the input here is going to take whatever is on here and shift it into this signal, which is 8 bits long. And it's going to take 7 down to 0. So the URX gets shifted into the most significant position. And then it increments bit sampled, because we're going to be looking for 8 to make sure that we're going to reach 8 bit samples. Then we're going to move on to the count 8 state. But first, let me explain that SURX data gets passed to the output here. So SURX data is actually being pushed out of here. So it never gets written to the register until we rewrite load high, remember. So in count 8, what we do is we look at S-bit sampled and check to see if we're at 8, and if we are, then go to a cleanup state where we finish up. If not, then go to a wait mod state. And we just wait 1 baud instead of 1.5 again, because since your sample is in the middle on this first data bit, we want to ensure that we're still in the middle for the second data bit when we sample. So that it transitions to the wait baud state, which waits a single baud length, and then once a baud length has been counted, it goes back to sample bit, which shifts in from the input again to SUR data, increments the S-bit sampled, and checks to see if we have 8, and repeats this 8 times until we do have 8 bits sampled. And then what will happen is that we go to the cleanup state, which will set sreg UART load high, which connects to this output. The output goes to this register to load the data that's on this output. And then it resets baud count, resets bit sampled, and goes to the wait out stop state. So once it's in state wait out stop, what we want to do is we want to wait for the stop bit before going back to the initial state. You might think that we should go to the initial state right after cleanup because there's nothing left to do. We already have the data that we want. Why don't we just go back to the initial state? Well, that would work, except for the time where your final data bit is